So in this video, we're going to look at the Earth. And if you're following along in the OpenStax book, in the astronomy book, it's chapter 4. So just to give you an overview of the things we're going to study, we're going to talk about the rotation of the Earth and how we know that the Earth rotates. We're going to talk about what causes the seasons. And we'll talk about the phases of the moon and what causes those, what causes the tides, and what causes eclipses. So these are some common astronomical phenomena that we can even see right here on Earth. So it's a good question of how do we know the Earth rotates? And we've known for a long, long time. It's certainly not a new discovery. And it's something called Foucault's pendulum. Now in this pendulum, they have, you can see it here. It's almost like a big bowling ball, a big heavy ball. And they have it secured to the ceiling. And they just start the pendulum swinging like a grandfather clock. But this is a pendulum that's just on a rope or a wire. So it's not the way a grandfather clock where it has to go a certain direction. And what they found, and many science museums have these, I think there's even one at the UN, where what they find is it moves as it rotates. Every few minutes they could see that it's not hitting the same sides or going to the same side. So maybe it's here 1 minute, and then maybe 10 minutes later it's here as it swings back and forth. So that gives a lot of evidence. Now another piece that we know, or we would need to know about, is what causes the seasons. And there's a lot of misconception about this out there. That's why I hope that, if you already know it, that's great. But if you don't, I hope I can clear some of the misconceptions up. The main thing that people get confused about, or they say, is, well, in the summer, we must be closer to the sun. In the winter, we must be further away from the sun. I mean, that seems reasonable, especially if you know that planets move in an ellipse or an oval shape rather than a perfect circle, because they don't move in a perfect circle. But it's actually not the Earth-Sun distance. That actually, the change between being closer to the sun and being further away is not as severe as people think. It's not severe enough to cause total changes of the seasons. What causes the seasons is the axial tilt of the Earth. So here's the Earth, and the axis isn't straight up and down. If we drew a line straight up and down, we would find that the axis is 23.5 degrees off of that. Now that dotted line axis, well, that would be perpendicular to how it moves around the sun. If we had a flat ellipse or oval moving around the sun, this dotted line would be perfectly at 90 degrees. But we're not at 90 degrees. We're about 23.5 degrees off. It does not vary throughout the year. Some people have this idea, and I even know myself when I was younger, I thought, well, maybe it moves and it wobbles back and forth. It doesn't. There is some movement, but it's about every 26,000 years. So on our lifetime scale, we don't worry about that. It's not wobbling. It's staying at the 23.5 degrees. Now, that's also the length of the day is going to also affect the season. So it is the axial tilt of the Earth, but also the length of the day. If you think about it, in the winter, we have shorter days. There's not as much time for the sun to heat up our atmosphere. In the summer, the sun's out longer. Just by being out longer, the rays are able to heat up the Earth more. So I think the best way to look at this, or to understand it, is to look at the diagram here. So what we call the summer solstice, June 21st, that's the longest day of the year. And on June 21st, if you look at the northern hemisphere, so North America, Europe, in the northern hemisphere there, we're leaning towards the sun. See how with the 23.5 degrees, we're leaning towards the sun. Whereas the shortest day of the year, December 21st, here's the northern hemisphere, and the northern hemisphere is leaning away from the sun. So it's not getting the direct rays. In the summer, we get fairly direct rays, and I'm going to show you a picture of that on the next slide. But in the winter, they're more diffuse because it's tilted away there. Now, equinox. Equinox means equal, or equi means equal. So this is March 21st is the vernal or the spring equinox, and the autumnal or autumn is September 21st. And those days are special because on those days in the spring and in September, every place on Earth has a 12-hour day and a 12-hour night. It's the equal, where night and day are exactly equal. But hopefully you can see in this picture how the tilt of the Earth doesn't change as it goes around the sun. Oops, I should have went the other direction. So in the summer, when, say, the northern hemisphere is tilted towards the sun, we're getting fairly direct rays here. They're a little bit at an angle, but they're coming down fairly direct. Whereas in the winter, you can see, in terms of the angle, it's more diffuse. The difference might be if you could imagine this as a hose. If you were hitting a hose, maybe you're cleaning a car. If you're hitting a hose and you hit the car pretty much straight on, it's going to have a lot of force or energy. Whereas if you angle the hose and you want to just maybe gently rinse something off, that's more like in the winter. And also, just to clarify in case I didn't say that, yeah, I focused on the northern hemisphere. We could have looked at the southern hemisphere. When we were having our summer, the southern hemisphere is having their winter. When we're having our winter in the northern hemisphere, the southern hemisphere is having its summer. Now, let's talk about what's special for the summer solstice. And there's this idea of this word zenith. And zenith basically means 90 degrees. So if you're standing on the Earth, this is going to be a real rough picture. The zenith is directly above you, 90 degrees. So on June 21st, which is the summer solstice, the sun is at its zenith, or at 90 degrees, at this special line that you've probably heard of, but maybe you didn't know why it was special. But it's called the Tropic of Cancer, or the line. Basically, tropic just means the line or the line of latitude. So at the Tropic of Cancer, so here we go, and you can see that passes through the northern hemisphere here. If you were standing right here, and the sun's over here, you would see the sun at the zenith, or 90 degrees, directly overhead on June 21st. And the other tropic is the Tropic of Capricorn, and that's in the southern hemisphere. It passes through South America. And there, the sun is at the zenith, as at the highest point on December 21st, what we call the winter solstice. Although if you were able to see it, if you were at the Tropic of Capricorn, for you, it would be summer, because it would be the opposite. So that's where we get the idea of Tropic of Cancer and Tropic of Capricorn, and why those are considered sort of special lines. Now, the length of our day. We tend to use the solar day, which is our rotation with respect to the sun. It takes 24 hours for the Earth to rotate on its axis and see the sun come back up. But there's this other term called a sidereal day. So think solar, sun, and sidereal. It's an odd word, but think stars. This is the rotation with respect to the stars. So instead of looking at the sun and saying, well, when does the sun come up and when does the sun go down, we could pick one of the stars and say, no, I'm going to use this. I'm going to use the North Star, or I'm going to use Betelgeuse, or some other star out there, or Altair. And what we find there is that because the Earth is moving around the sun also, there's this shift. The sidereal day, which astronomers tend to use, they tend to prefer the sidereal day, is 23 hours and 56 minutes. So any particular star that you would want to follow, let's say Altair, if you want to follow Altair, which is one of the stars in the sky, it would rise 4 minutes earlier every night. It's also worth talking about, since we're dealing with time here, is, well, where did we get our calendar from? The tropical year, or what we use, it's actually 365.2422 days to go around the sun. So 365 and roughly a quarter days to go around the sun. So that's where we had the idea of a leap year. And we've actually had leap years for a long time. Like I said, longer than people think. In the Western world, the predominant calendar for many, many years was the Julian calendar, named for Julius Caesar. Now, I don't know if Caesar himself came up with it, but it was put into place during his reign as a Roman emperor. And they used 365.25 days. And they'd need a leap year. So every 4 years, you'd need a leap year to catch up. The problem was his calendar was in error by 11 minutes a year. To you and I, and at first we think, well, 11 minutes doesn't sound like much. But over the centuries, it started to add up to days and days and days where things just weren't working out. So the Gregorian calendar was Pope Gregory the 13th, and he was a contemporary of Galileo, just to show you roughly when he lived. And the reason he was, you say, well, why is the Pope interested in calendars? Because as a religious leader, he wants the holidays, the different religious holidays and feast days, to fall on at the same time every year. He doesn't want to have Christmas and Easter jumping around because the calendar is all messed up. So he adjusted the leap years, and this is the current calendar that we use. There's been some tweaks since then, but it turns out that it's actually not every 4 years, and there's a formula to figure it out. The place where it is usually is if it's 100 year. So I believe the year 1800 was not a leap year. So there's certain 100 years that are not strictly leap years. We're not going to worry about the mathematical formula, but it's a common misconception. Every 4 years actually isn't a leap year. Phases of the moon. And this is one that there can be some misconceptions about. And the main misconception that people have is that the phases of the moon are caused by the shadow of the Earth. But here's where it falls apart. This is what we call a gibbous moon. And it has nothing to do with a gibbon, which is a type of ape. But notice the gibbous moon. It's, kind of circular here. There's no way the shadow of the Earth could cause that kind of shape, because the Earth, in order for that to work, see, the rest of the moon is here, but in order for that to work, the Earth would have to be shaped like a crescent or a banana. So the real reason we get phases of the moon is the motion of the moon relative to the sun. Let's put that in a little bit more layman's terms. The reason we see the phases of the moon is because what we're seeing is how much of the moon, what part of the moon, is lit by the sun. And it's unequal. Throughout a given lunar cycle, roughly a month, not exactly a month, a little shy of a month, the moon is not being lit exactly the same by the sun. And also, this is just best explained with an image. So this outer ring, these outer ones, that's not the moon. That's what we see. The inner ring shows the moon moving around the Earth here. And it's about 27 days, 27 and a little bit more. So you might think, all right, point E here. So if the sun is over here, let's draw a little sun here. It would be much further away, of course. You would think at point E, well, you'd get a lunar eclipse because the Earth would be blocking the sunlight here. But that's only at certain times. The moon's actually, the ellipse is tilted a little bit, so you don't always get that exact perfect eclipse. Only there's certain times when you have them. So when you get a lunar eclipse, that's during a full moon. Because during the full moon, you see all of this face of the moon is lit by the sun. Now the gibbous is the circular illumination. And waxing means it's increasing. And so when something wanes, it means it's decreasing. So as it's coming in this direction, okay, let's start here. See, this is the half moon at point C. We see half of it. Then as the moon moves over here, it's getting even more sunlight, and we're seeing it waxing gibbous, getting bigger and bigger, and then we can see the full moon. Then when it moves over here to point F, we see that it's waning, that the spot's getting smaller and smaller. And then here, we're only going to see half lit and all the way. Now, how about that's for a lunar eclipse. I know it's not on the slide, but let's talk about a solar eclipse. You're only going to get the solar eclipse during a new moon. Because the new moon, we don't really see much of it. It's very dark. But that's the only time when the moon is up during the day, when it's a new moon or pretty close to a new moon. And that's the time when it could block it out. So when you see the moon during the day, it's either the new moon or you can see it's the waxing or waning crescent is usually what you see. And the crescent is the C shape. That's why it's called a crescent. Just like a crescent roll. So the moon's solar month is about 29.5 days. That's the time for the phases of the moon to repeat. But the moon's sidereal month, so remember, solar has to do with the sun. Now in this case, sidereal more has to do with the Earth. We're using the Earth as the reference, not the sun. Is 27.3 days. That's the time it takes to go around the Earth with respect to the sun. Now, why aren't they the same number? It's caused by this eastward motion of the Earth, because we're moving around the sun. In practical terms, what this means is the moon rises about 50 minutes later each day. So if it rises at 9 o'clock one day, it'll rise 9:50 the next day. And then the day after that, what would that be? 10:40, and so on. And it just keeps rising later and later each day. So there are many nights where you don't even have a moon. You don't have a moon every single night. So the moon's synchronous rotation. This is a neat thing. The moon rotates on its axis in exactly the same time as it takes to revolve around the Earth. And, there's some speculation this may have to do with the moon's origin, and that's how it's sort of locked to the Earth. So what that means is as the moon's going around us, it's rotating also. In a way, it's almost like Ptolemy's epicycles. But it's not wobbling, it's just the spin of the moon. And what this in practice means is that the same side of the moon always faces the Earth. We can't see the dark side of the moon, or what we call the dark side of the moon. However, there actually is no dark side of the moon. Let's place the sun over here. So we only ever get to see what we call the light side of the moon. But when the moon is in front of the sun, that's our new moon, this is actually dark. The side we see is dark, and what we call the dark side is lit. So that there is no dark side of the moon. The dark side absolutely can be lit. We just don't see it. And it was kind of a big thing when we first sent up different spacecraft to see the moon, and we were able to actually get pictures of the dark side of the moon. And that was kind of exciting because you could never in human history see it from the planet. You have to do it from a spaceship. And there were no alien bases there or anything like that, fortunately or unfortunately. So a couple more things to take care of, and one is the tides. A real misconception that people can have is, the tides are caused by the pull of the moon on the waters of the Earth. True, but it's also caused by the pull of the sun. The sun is big enough to keep the Earth in its orbit. It's also big enough to pull on the waters of the Earth. And the tides are twice daily. It's a twice daily pattern. Now, why does it affect the fluids? It's able to affect fluids like gases, so it could affect the atmosphere, but we're going to focus on the water, not solids. It's really not having a huge effect on the solids like the land masses. It's caused by universal gravitation. It's called a tidal bulge. And we'll see that in the next slide. Now, the sun's pull is only about half of the moon's. The sun is really, really big. However, it's also really, really far away. Our moon is much, much closer. So when the moon and the sun are on opposite sides, you get that spring tide. And it could also be true if the moon and the sun happen to be on the same side. You'd get also the spring tides. And my drawings here are a little exaggerated. So spring tides do not have anything to do with spring, the season of spring. Because think about it, as we said not too long ago, spring can be different in the northern and the southern hemisphere. Spring can come at different times. Spring tides are tides that are very high because the tides spring up. So if the sun and the moon are on the same side or opposite sides, they actually reinforce this tidal bulge and they pull on the water more. In this picture, we're imagining the Earth as a perfect sphere, but it's not. So the tides are a little bit different in different places because the ocean has different depths, so the water can be at different depths. So the effect isn't exactly the same all over the Earth. That's why there are tide charts. There actually are. If you're someone if you ran a fishing boat or live near the ocean and you had a boat and you need to worry about that, there are books and tidal tables. I'm sure it's all online now, but we'll tell you when the spring tides and the high and low tides are. Neap tides, so spring tides are especially high. Neap tides, the tides are not as severe. They're lower. That's not low tide. There's a high tide and a low tide. There's two of those every day. But spring tides are really, really strong tides. Neap tides you could think are really, really weak. And the reason is the moon and the sun are pretty much at right angles there. So they're not able to pull in the same direction, and their effect partially cancels out. So we can see the tide here, and this would happen twice daily. You can see in this picture, okay, the tide was way up to here, but then it goes out, and if I draw that line at about the same spot, you can see the water's not there, and the boats now are sitting down there in the mud, so they wouldn't be able to go out into the ocean. And then we'll talk a little bit about eclipses. And there's two types of eclipses. One is the solar eclipse. And again, the solar eclipse is caused by a new moon. That's when the moon is on the same side as the sun. So here's the moon, and it blocks it. Now there's two types. Oh, I should also mention, the darkest spot is called the umbra. So the umbra would be right there in the center. An annular eclipse, in an annular eclipse, the moon is a little bit further away from the Earth. The moon's orbit, as we said when we talked about Kepler's law, is also an ellipse. The moon doesn't go in a perfect circle. So there's times when it's a little further from the Earth, times when it's a little closer. So when it's further from the Earth, it's a little smaller in our sky, and we get what's called an annular eclipse. And in an annular eclipse, you have this ring around the edge. You get the outside light ring. The total eclipse, I believe they're rare, is when the moon is near to the Earth and you get complete coverage. Now, you don't see, when you have a total eclipse, it doesn't take place everywhere. So it's not like the whole planet sees this eclipse. So that's why there are people who they chase these eclipses and they travel. I knew a fellow last time there was the total eclipse, and he drove to one of the southern states. I don't remember where he went, one of the Carolinas or something, but he went much further south, but he's retired, so that he could actually get to see the eclipse. But here's a little point that really doesn't have much to do with the science, but I still think I need to say it for safety. Do not look directly at an eclipse. You cannot look directly at an eclipse with your eyes or your eyeglasses, or even if you have sunglasses. Don't do that. They make special eclipse glasses that block it out, or there's ways to see it looking at it like through what's called they put a pinhole in a like in an index card, and you can project it on the sun. So don't look directly at an eclipse, because even though the sun is partially blocked, some of the rays can still get through. And just to give you, never with the binoculars or a telescope, and just to give you a word of warning, Galileo went at least partially blind in his later years from looking through telescopes at the sun. So we never do that. And then the last thing we're going to discuss is the lunar eclipse. These are more common, and you don't have to travel. Anyone on the night side is able to see it when we get it. So there's no geographical limitations. And that's when the moon passes through the Earth's shadow. Again, this is an eclipse. This isn't the phases of the moon. So in this case, the Earth, here's the ray of light from the sun, the Earth will block it out. These are perfectly safe to observe because you're not looking at the sun. You're looking at just the moon. In the same way, it's not dangerous to look at the moon. You can look at the moon. In fact, if you have binoculars, look at the moon sometimes, like when you have a full moon or crescent moon or something, and you can even see some of the craters and the features because you're only looking at the effect of the sun's light reflecting from the moon. And when you get a lunar eclipse, it's only during a full moon.